Hello, and welcome to the presentation on risk-averse controller design against data injection attacks on actuators for uncertain control systems. I'm Sri Balaji, and this is a joint work between me and Andre, and we are from Uppsala University, Sweden. The outline of this presentation is to introduce and motivate the problem, which is a design problem, and then we reformulate the design problem because it's non-convex, and then we approximately provide a solution to the formulated design problem. Finally, some conclusions on our work. The number of vulnerabilities on industrial control system has been ever increasing since 1997, as you can see in this picture. A couple of examples include the Black Energy 3, which was a denial of service attack on the Ukrainian power grid in 2014, and Industroyer in 2016. So to counter such attacks, we consider the following setup. We consider a network control systems where a process is on one side of the network and an anomaly detector and a controller is on the other side of the network. In this setup, we consider an adversary with perfect system knowledge injecting an attack into the actuator channel of the control systems, but the aim of the adversary is to increase the performance cost while staying undetected. In general, the operator tries to keep the performance cost low, similar to LQ control. With this setup, we provide the following contributions. The state of the art in the current literature is to design controllers to minimize the attack consequence in deterministic system. Whereas we design controller to minimize the attack consequence for uncertain systems. To see this more clearly, this is the result of our paper, where we take 100 different samples of the uncertainty, and we show that under the optimal controller, the value of the attack impact is significantly reduced. Here, the red line represents the median of the attack impact across 100 different uncertainties. When the optimal controller is used, this median is lowered significantly. And in the rest of this presentation, I will explain how to design this optimal controller. To begin with, we considered this system, which is a linear time invariant discrete time system where there is process uncertainty. Here, the process uncertainty is a parametric uncertainty, where delta comes from this bigger set, omega. We consider a static output feedback controller and an observer-based detector. The signals are that the input is U is the control input and U tilde is the control input plus the attack. Since we consider U tilde as control plus attack, we actually consider data injection attacks in this work. So we can rewrite this system as a closed loop system where the main input is the attack and the system outputs are the performance output and the residue output. To recall again, we consider a setup where the adversary has complete system knowledge. So he knows the system 1, 2, and 3 without any uncertainties, or he knows the exact value of the process matrix A instead of this uncertain matrix. Whereas we consider an operator who's uncertain about the process. This setup helps us study the worst case, although it might be unrealistic. So again, coming back to the aim of the adversary, an adversary with complete system knowledge injects false data into the control signal to increase the performance cost while staying undetected. This increase the performance cost can be mathematically translated as the increase in the performance energy whilst keeping the residue energy low. Here we consider 1 without loss of generality. This can be made into any epsilon. So the optimization problem of the adversary who is trying to maximize the performance cost while staying undetected is 4. Here, the adversary can exactly solve this problem since he or she knows the exact value of delta. He or she does not have uncertainty in the process knowledge. However, if you consider the same optimization problem for the operator, he or she does not know the exact value of Q, whereas it becomes a random variable. So the operator tries to design the controller such that the value of this random variable is always low. So in order to counter this uncertainty or this randomness in the variable Q, the operator uses a risk metric. Here we consider conditional value at risk. So once again, what the operator tries to do is that he or she tries to design the value of the controller K such that this risk metric is minimized. So that is the main design problem that we consider in this paper, and we try to provide an approximate design solution. To give an intuitive idea of what conditional value at risk is, as you know, value at risk is the probability. So if you consider a random variable, value at risk represents, so if the value at risk is beta, it means that the probability that the value of the random variable is higher than beta is 1 minus alpha here. And conditional value at risk is the expectation of the tail above value at risk. So this is an intuitive idea of what conditional value at risk is. Here, alpha is a given design parameter. So it's given beforehand to the design problem. It's also called as the risk threshold. So now we reformulate the design problem. We reformulate the design problem because the variable Q is non-convex in K. So what we try to do is that we try to derive an upper bound for this Q, say Q bar. We show that this Q bar is strongly convex in K, so that in the optimization problem 10, we replace Q with Q bar. So as a first step, or this is the first result of the paper, we show that Q is upper bounded by Q bar, and mu is a term independent of the controller variable, and Q bar is this guy, where F is the Frobenius norm, sigma is the singular value, and K is some function of the system matrices. And we first prove this in the paper. Secondly, we show that the function Q bar is strongly convex in the design variable K. So why we do this is because in the design problem, the non-convex part can be replaced by this convex part Q bar. So this is the design reformulation that we do first. Secondly, we provide an approximate design solution. So using the definition of conditional value at risk, the design problem can be written as shown here. But here you can see that the expectation operator operates over a continuous set omega. And it is difficult to solve this explicitly since the set omega is continuous. So what we do is we take a discrete set omega n. So we approximate the set omega with a discrete set omega n, where n represents the number of samples in the discrete set, and then study the guarantees of the solution. So in this paper, the optimization problem 12 was reformed for discrete set omega n, was proven to be equivalent to the optimization problem 13. And this is convex because Q bar is convex, as we seen before. So this is the final design problem that we approximate our initial problem as. We do provide some guarantees or probabilistic certificates on the solution that we obtain. However, I don't discuss it here due to the time constraint, but if you're interested, please see the paper. I essentially show that the probability distribution of Q bar under this controller is a beta distribution. Next, we consider an example, a numerical example, where these are the system matrices and A and B are the uncertain parameters. We choose the horizon length for norm as 5, and then the number of samples to approximate the discrete set as 11. And we obtain the value of risk. Here, M represents the risk threshold alpha, but for the discrete set. So there is a method to convert the risk threshold from the continuous set to the discrete set. And in reality, the confidence can be made higher by increasing N or decreasing M. Here by confidence, I mean the probability, the distribution confidence. Next, we see this. This plot as I showed in the beginning of the presentation. So now I described a way to obtain the optimal controller using the discrete set. And as you can see, the median is significantly lowered. So thank you for listening to this presentation. So in this presentation, we consider data injection attacks on actuators, where an adversary tries to increase the performance cost while staying undetected. And we propose a convex optimization problem to solve the design problem with probabilistic certificates. And we illustrate the results through a numerical example. This is my mail address, and if you're interested in any of my other works, here's my homepage, and I would be happy to take any questions.